Hello everyone, my name is Junpeng. I am a PhD student at Purdue University. Today I will present HubBub, contention-based sectional attacks on USB hubs. This work is a collaboration between Purdue and CHK. As we all know, hardware sharing exposes attack surfaces for a lot of sectional attacks. For example, flash and reload relies on memory sharing, prime and probe relies on LLC sharing, tailblade relies on TLB sharing. And there are many other sectional attacks relies on the sharing of CPU ports, CPU interconnects like mesh and ring, PCI links, and memory controllers. Since hardware sharing improves system flexibility and reduces costs, it's hard to fully eliminate them. In this work, we investigate another target, USB hub, which also presents a hardware sharing scenario. Besides, it is widely used in our daily life, especially on recent laptops with fewer and fewer USB ports. Now, this picture shows a typical USB hub. There are multiple downstream ports, such as USB A and C ports, HDMI ports, network interface card ports, and USB power delivery ports. But there is only one upstream port, which means that multiple devices must share the same USB bus. Based on this, we propose HubBub, which is a new class of sectional attacks based on USB hub contention. HubBub explores potential information leakage on USB 2.0, 3.0, and 3.1 hubs. In our evaluation, we can show that HubBub can leak information from at least 3 USB peripherals. They are NIC, camera, and keyboard. The threat models of HubBub are straightforward. First, we assume that multiple USB devices are connected to one single USB hub, as illustrated in these two diagrams. Then the attacker can take two forms. As shown in the left, the host-based attacker is a malicious software running on the host. It has access to at least one USB device. Such an attacker can run directly as a normal process, or it can be isolated in a virtual machine or web browser. Then, as illustrated on the right, the device-based attacker is a malicious USB device physically attached to the USB hub. Here is an example of a HubBub attack, referred to as Attack A in the paper. The goal of this attack is to infer which website the victim is visiting. In this scenario, we assume that both a USB network interface card and a USB SSD are connected to the same USB hub. Then the attacker controls a program with access to the SSD. Then the program can either be a standard process or isolated within a virtual machine. Meanwhile, the victim is browsing websites using the USB NIC. Then, by exploiting shared USB resources, the attacker attempts to extract information about the victim's web activity. There are three main steps to launch the attack. Step one is that the attacker program attempts to saturate the USB hub's bandwidth. To do this, they can utilize Uring or other frameworks to perform high-speed SSD accesses. The picture below shows our throughput analysis on a typical USB 3.0 hub. The x-axis represents the I/O size used to access the SSD, and the right y-axis shows the throughput achieved by our attack program. As the red line shows, the theoretical bandwidth is 5 Gbps. However, due to encoding, packet framing, and flow control overhead, the actual effective throughput is around 3.2 Gbps. As the graph shows, when the I/O size is adjusted to 4 KB, the program is able to saturate the USB bandwidth, which is important to the success of our attack. In the second step, the program records the timestamp for each I/O accesses using RTTI-CP, then calculates the intervals between them. When the victim accesses different websites, it generates different network patterns. These patterns cause varying levels of congestion on the USB hub. This picture shows traces collected when accessing different websites, and we can clearly see that the patterns are distinct. The third step is to pre-process the traces and train machine learning or deep learning classifier. With the trained classifier, we can identify which website the victim is accessing. We first evaluate this attack on the USB 3.0 hub. We select the top 100 websites and collect over 500 traces for each website. We then split the dataset for training and testing. After that, we train a GRU and attention model on the training set, and then we achieve over 98% accuracy on the test set. After the one-hub evaluation, we also confirm attack A works on 10 USB 3.0 hubs, 4 3.1 hubs, 1 2.0 hub, 1 internal hub, and 1 monitor with the USB hub functionality. The internal hub is typically soldered onto the motherboard and is connected directly to the USB controller. Other evaluations and results can be found in our paper. Here is a recap of attack B. The goal of this attack is to infer activities captured by the web camera. As shown in the picture on the left, a USB NIC and a USB webcam are connected to the shared USB hub. The attacker is a JavaScript program embedded in the web page. Then the webcam is activated and monitoring a rule. As the traces on the right show, the attacker can distinguish patterns such as whether the light in the room is turned on or off. Details of this attack could also be found in our paper. Here's a recap of attack C. The goal of this attack is to capture keystrokes from the keyboard. As shown in the left, a USB keyboard and the attacker's USB device are connected to the same USB hub. Then the user will type some sensitive text on the USB keyboard. By monitoring the traffic on the shared USB hub, the attacker can infer keystrokes, as shown in the right picture. Further details can be found in our paper. This project is funded by NSF. Thank you for your attention.